Hi everyone, so today I'm going to be going over exponential functions again. So if you're still with me, this should be video number 3. And what we're going to be looking at is how to tell which model, either exponential or linear, is a better fit of the data that we're talking about. So here's an example. The number of branches on a large tree after the decade of 1850 is represented by the following table. So they give you a table. Now remember, they could give you the table, this is vertically, they could give it to you horizontally, so don't freak out if they do, okay? And they ask which model, be it T, the number of branches T decades after the decade of 1850 best fits the data. Well, first of all, don't be frightened. Remember, that's just function notation, so they're looking for a function. They're basically telling you it is a function, and that T is going to represent our X, and be it T is going to represent our Y. Okay, so then I look at the answers, and I notice that I have 2 linear functions, and I have 2 exponential functions. So these are in the form y equals b plus mx, and these are in the form y equals ab to the x. So really, the easiest way to approach these problems is to determine if they have a slope or if their rate of change is a percentage. So how do you do that? Well, if it's a slope, you just take the change in y over the change in x. So for me, what I do is I subtract my x's and my y's. So I'm going to subtract my y's. So I'm going to do 49 minus 31, which gives me 18. I'm going to do 66 minus 49. That gives me 17. 85 minus 66 gives me 19. Okay. And then 102 minus 85 gives me 17. And 120 minus 102 gives me 18. And then I noticed that all of these were changing. Their difference was 3. So to be quite honest with you, these numbers are all really, really close. So I'm going to go with that this is a slope, a constant rate of change, okay? Especially because if I do the ratio, that means I would do 49 over 31, and I do 66 over 49. Let's see if those are close. And then I'm going to do 85 over 66. And this is what I would do if I were determining if it were exponential. So let's see what happens if I get those ratios. Because remember, the ratio between the terms would be the same or close to it if it were exponential. So 49 divided by 31 gives me 0.58. 66 divided by 49 gives me 1.34. 85 divided by 66, and actually let me go back to full screen. 85 divided by 66 gives me 1.28. So these are actually going down, but they're not even close, really. 102 divided by 85 gives me 1.2. And 120 divided by 102 gives me 1.17. Okay, so look at those. Those are not necessarily close ratios. They're very different. There's a difference of almost 30% there. Whereas here, 18 over 3 and 17 over 3 and 19 over 3, they're all pretty close to a slope of 6. So I look carefully at my numbers. I determine it's not exponential, it's linear. All I have to do is see the slope. And we already know our y-intercept is 31 because there's that x of 0. So my answer would be B. So think about just looking at the differences. I went through a lot of steps there because I wanted you to see the difference between finding a slope and finding a common ratio for an exponential model. All right, so we could ask you, or I could give you something like this, where I ask you to determine whether the data described in tables is best modeled by a linear or an exponential function. So again, you're going to go through that process. I'm kind of looking at the car and I'm wanting to say it's exponential because look, it's going down about 35, we'll say, right? And this one's going down about maybe 16, 17, and then this one's going down by 8, and this one's going down by 4. So I can see already it's not going down at a constant rate since all the x's are going down by 2. So that's not going to be linear. But what I can say is 34 over, I'm going to round here, 34 over 69, 17 over 34, 8 over 16, I'm going to do it like that, and then 4 over 8. I can see these are all going down by a ratio of about almost close to a half. So this would be an exponential model. And think about that. If I multiply 8.2 by a half, I'm going to get about 4, right? All right, so the train. We want to look at the train as well. Again, all those x's, these were all going down by 2 or up by 2. These are all changing by 2. So yeah, I would like to see if it's linear. So I am just going to check 88.9 minus 50.1. So it's going down by 38.8. And then from 50.1 minus 28.1, it's going down by 22. And then from 28.1, you can even just see this, right? 15.8, it's going down by 12.3. So I could already tell it's not linear. So, but you want to be careful. It doesn't have to be exponential. I'm just asking you if it's linear or exponential. This one is not, so I'd be looking at the ratio. So I'd do 50.1 over 88.9, 28.1 over 50.1, 15.8 over 28.1. 8.5 over 15.8. Now this one I use the exact numbers, but I could round. I could do 50 and 89. I could do 28 and 50. I could do 16 and 28. I could do I might do 9 and 16. Let's see what happens. 50 divided by 89 is 0.56. Okay. 28 divided by 50 is 0.56. 16 divided by 28 is 0.57, again, but still really close. And 9 divided by 16 is 0.56. So you can see now that this has worked out to be a constant percentage or a constant ratio, so it is an exponential function. All right, guys, I hope that was clear. It's just kind of I'm expecting you to have some, basic prior knowledge on this. So hopefully this was just a little bit of a review for you to how to tell the difference between the two. All right, have a great night.